All right, guys, took a little break. Now let's look at some common sequences. So we are still in 11.1. This is part 2, technically part 3, because part 1 I had broken in half because of a phone call. Uh-oh, I forgot to put my phone in Do Not Disturb, so let's hope I can get through these without my phone ringing again. Anyway, some common sequences. 1 over n. 1 over n is just simply the sequence 1, 1/2, 1/3, 1/4. This is called the harmonic sequence. Right, and the harmonic sequence converges to 0. So when I talk about the harmonic series, we'll always be talking about 1, 1/2, 1/3, 1/4, so forth and so on. -1 to the n power over n. This is an alternating sequence. The -1 to the n power just alternates back and forth between positive and negative numbers. So if n is 1, we get -1 over 1. So the first term would be -1. If n is 2, we're squaring -1, so it would be +1 over 2. So it looks very similar to the harmonic sequence, but we're going to switch back and forth between positive and negative terms. So the signs alternate. Here the odd terms are negative, the even terms are positive. This is called the alternating. Harmonic series. Nope, harmonic sequence, sorry. Okay, we can also do -1 to the n plus 1 term over n. This is also called the alternating harmonic sequence. The difference is that the odd terms will be positive and the even terms will be negative, because if n is 1, the power on -1 would be 2, and this would be 1 down here, so it would be +1, -1/2, 1/3, -1/4. So this is also called the alternating harmonic sequence. So you might say, well, when do we know which one it is? Well, either one of these is called the alternating harmonic sequence. So it would give you which one it wants you to work with if necessary. All right, so harmonic sequence, all terms are positive. Alternating looks like the harmonic series, but it just switches between positive and negative terms. Okay, a geometric sequence is a constant times a number to a power. Both of these stay constant. So R here is called the common ratio. So hopefully you talked about this in your pre-calculus class. Maybe we have something like we start with 8, and then we're down to 4, and then we're down to 2, and then we go to 1. Not sure if you can see the pattern here, but to get from 8 to 4, I multiplied by 1/2. To get from 4 to 2, I multiplied by 1/2. So the common ratio here would be 1/2, 1/4. So this would be 8 times 1/2 to the, oh, interesting. Yep, I'm going to do this. There's different ways I can write this. Now notice I didn't call this n, because if I called this n, I wouldn't get my first term of 8. So we could also write this as, there's different ways to write this. If I put it into this form, it would be 16 times 1/2 to the n in order to get my first term of 8. So if I started this at 1 to infinity, so there's different ways to write it. In the end, it's all going to work out the same for our purposes. So these are two different ways to write this geometric sequence. What's really important that we need to identify is the common ratio, which is 1/2. So to get from one term to the next, we just multiply by 1/2. It's called the common ratio because if you take the next term and divide it by the previous term, that's the ratio it's referring to. So 4 divided by 8 is 1/2, 2 divided by 4 is 1/2, 1 divided by 2, so forth and so on. So that's where the term common ratio comes from. 2, we could have something like this. I could have, let's start with 2, and then I could have 6. I could have 18, 54. Right, so to determine if this is a geometric sequence, if you don't see it, you take 6 divided by 2. That would give me a ratio of 3. 18 divided by 6 would also give me the ratio of 3. 54 divided by 18 is a ratio of 3. So this is a geometric sequence. Common ratio would be 3. So we could write this as first term 3 to the n minus 1 power to give me the 2 to start with. And we start with 1 to infinity, because then if I put in the 1, this cancels out and gives me the 2. Or I could write this as 6 times, nope, sorry. No, what would it be? Nope, I can't do that, because then if I do this, that actually gives me that term. So how would I write it if I wanted to put the n up here? How about we do, it would have to be 2/3 times 3, right, to the n maybe? Because if n is 1, that would give me the 2. Yep, so that would work. N equals 1 to infinity. Right. We're going to like this form better, so we'll talk about this a little bit later. But either one of these is going to produce, either one of these templates will produce that sequence. All right, so geometric sequences, we can generalize how these behave. If we look at this guy, notice that my terms are converging to 0. Here, notice my terms are shooting off to infinity. So in general, a geometric sequence will converge to 0 if your common ratio is between 1 and -1. So as long as it is a value between 1 and -1, we often write it like this instead. The absolute value of r is less than 1. The geometric series converges to 1. Oh, nope, sorry, because I'm looking at it like this. It's going to converge to a if r is equal to 1. So for example, if we had 7 times 1 to the n, this corresponds to, at n is 1, it's 7, 7, 7, 7. So it would just be, not very interesting, the constant sequence 7. So it would converge to that value right here, a, and the limit of 7 times 1 to the n is equal to 7. And then it diverges otherwise. So, in conclusion, the geometric sequence converges to 0 if this, the absolute value of r, the common ratio is between 1 and -1, converges to the constant out front if r is equal to 1, and diverges otherwise. Let's see, do I have anything else interesting to say about that? All right, some commonly occurring sequences and their limits. So these are going to be handy, so make sure you kind of rabbit ear this page in your notes, because for our next few sections, we're going to refer back to these. Like, oh yes. All right. The sequence, the natural log of n over n. Well, this converges to 0. And how do I know that? Well, if I look at the function f of x is natural log of x over x, because sequences behave like their corresponding functions, right? If I take the limit as x goes to infinity, the numerator goes to 0. The numerator goes to infinity and the denominator goes to infinity. So we can use L'Hopital's rule here. The limit as x goes to infinity, the natural log of x over x, because it's an indeterminate form, infinity over infinity. The limit as x goes to infinity is the derivative of the top over the derivative of the bottom. Now we can only use L'Hopital's rule if it's an indeterminate form of infinity over infinity or 0 over 0. So this is the limit as x goes to infinity of 1 over x, just using algebra. And that limit, so LH is L'Hopital's rule. And that would be 0. So this sequence, we can conclude that the natural log of n over n converges to 0. You can use that as a fact now. This one's a little bit trickier. The nth root of n. So if we looked at this, this would be the first root of 1, the square root of 2, the third root of 3, the fourth root of 4, so forth and so on. Okay, this actually converges. You can pop it into your calculator, but it converges to 1. And this one again is going to be a little bit handy in our series talks later. So if you want to know why, I think this is kind of pretty cool. Well, the nth root of n is equal to n to the 1 over n power. But by properties of logs and exponents, this is so cool. Right? Because e to the natural log of anything is just what's inside the natural log. But now I can bring this power out front. This is e to the 1 over n, natural log of n. But this is e to the natural log of n over n, and we just showed up top that this goes to 0, and e to the 0 is 1. Right? So this is the nth root of n converges to 1. So again, keep that in your little side notes. If you have the nth root of a constant, the nth root of a constant converges to 1 also. I'll leave the proof of that up to the reader. If you want to do it, it's very similar to the previous one. So for example, let's suppose we had the nth root of 4. The nth root of 4 is actually going to converge to 1. And then another common limit is 1 plus c over n to the n. We talk about this back in Math 172. This actually converges to e to the c. So e is often defined by using this little template, and using x instead of n. So for example, if you had 1 plus 3 over n, all to the nth power, that converges to e cubed. So again, this template is going to come in handy. And then one other little blurb of information for this section is factorials. I'm hoping at some point in your math career you've worked with factorials. So by definition, n factorial, which is n exclamation point, only defined for integers. Non-negative integers. Is that number times the previous integer times the previous integer, and you keep going all the way down till you're at 2 and 1. So for example, 4 factorial by definition is 4 times 3 times 2 times 1 is 24. Well, 10 factorial gets really big really quick because that's 10 times 9 times 8 times 7. All the way times 2 times 1. And I'm not going to take the time to do that, but if you look here in your calculator, you can, if you have one of these handy dandy graphing ones, which you should, if you go under math and you go over to PRB, the fourth one down, number 4, is factorial. So 10 factorial is going to be 3,628,800. Okay, a couple notes. 1 factorial is 1. 0 factorial is actually equal to 1 also. I think that's a pretty cool little fact. All right, want to see why? I know, I think this is kind of fun, right? So notice 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1, right? But this is just 6 factorial, agree? So 7 factorial is 7 times 6 factorial. So do you agree we can do this with any number? So therefore, 8 factorial is just 8 times 7 factorial. 100 factorial is just 100 times 99 factorial. All right, so keeping that in mind, any number factorial can be n times its previous number's factorial. Right, so then if I take n factorial and divide it by n, that's the same as n times n minus 1 factorial all over n. These cancel out. So n factorial over n to go to n minus 1 factorial. So let n equal 1. Then 1 factorial over 1 is equal to 1 minus 1 factorial. 1 factorial over 1 is 1. 0 factorial. There you go. Proof that 0 factorial equals 1. Okay, so this is also going to become handy too. Keep this in mind too. That little template. All right, so that's it for 11.1. To do. Read 11.1 in your text. Exercises 3 to 53 odd in your text. XYZ homework. Oh, shoot, let me look up quickly the corresponding section for this. Let's see if I can get to it quickly. I don't think I have it up. See Blackboard, I think it's 5.1. I'll look quickly for you if you want to wait. If I can get in, Blackboard's up and running nicely. Looks like it is. So if you look in your announcements, 11.1 is not a section that's offered in XYZ. It's a different section number. So it's going to be your job to look at that corresponding sequence. It's in the announcements. I gave you a table that connects the two. So let's see. 256. No, boy, it's way off. All right, so see Blackboard for corresponding section. I believe it's 5.1, so I don't know, my Blackboard's doing weird things right now. So I'm gonna end there, guys. Have fun. Don't forget to Zoom in if you have questions. I will be here from 12:30 to 1:30 on Zoom if you want to do some problem solving. We can try to start setting that up on a weekly basis if you'd like to do that like we did in class. All right, hope everyone is well. Miss you guys. Stay safe, stay inside, and I will hopefully see some of you soon in Zoom. Bye.